So I was running some trails the other day. I was running up on in the hills, and while I was doing it, I was thinking a lot about the ways in which my legs need to push at different times while I'm running in order to kind of propel myself how I want to, right? So you can think about it like essentially when I'm going on a flat versus uphill versus downhill, there's different ways in which my body needs to be propelling forward. When I'm on a flat, I need to go just directly forward. Like in this diagram, you can see that that's to the right, right? Whereas when I'm on an uphill, I don't just want to go forward because that's going to run me into the hill, right? I want to go kind of following the path, right? I want to follow the ground and go in this sort of upward to the right direction. And when I'm going downhill, as you might have guessed, I want to go down the hill. So I want to kind of go down into the right. So these blue arrows represent kind of my goal, what I want my body to do, right? Now, when I'm doing that and I'm thinking about how my legs should push at these in order to create these different effects, I need to think about not just the force that my legs are going to enact, but also other forces that are upon my body, namely the force of gravity, right? Gravity always pulls us down towards the center of the earth. So gravity's pulling me downward here at the flat, gravity's pulling me downward at the uphill, and gravity's still pulling me downward on the downhill, right? It's always pulling me the exact same direction down, right? So what happens is because of this, I need my legs to essentially be pushing myself in a way that will counter this downward force of gravity and as a result propel my body the direction I want to go, right? So in order to do that, I would actually need, this is why when with our legs when we're pushing while we run, we actually push in a bit more of a diagonal direction, right? Because when I'm pushing diagonally and then I take into account the gravity that's affecting me, the result is me going forward, right? If all I did was push to the right with my legs, you can envision if I push to the right with my legs and gravity's pulling me down, where is my body going to go? It's going to go in a diagonal direction and I'm going to eat some shit, right? So because I don't want to do that, I am going to instead push, I'm going to instead push diagonally because that's going to give me the direction I want to go. Now, when I'm going uphill, like let's look at a different scenario, right? If I'm going uphill, right, gravity's still pulling me down, but the goal is for me to actually go a bit more upward. So what happens is my legs actually need to push with a lot more upward force, right? You can see this arrow for the force of my legs is much more upward. And what's going to happen is, as a result, I will have a more upward trajectory, right? And similarly, if I want to go downhill, gravity is actually helping me here, right? Because I want to go downward a bit, I can actually utilize gravity. This is why we're able to run so much faster when we go downhill, because what I can do is I can actually instead focus all of my effort on going to the right, and the effect of gravity will help me going downward. I don't need to actually push down really, right? Now, this is all sort of to introduce to us a topic that are of what we call vectors. So every single one of these arrows that I've drawn in this diagram, every single one of these forces that we've been discussing, they represent things that we would call vectors. Let's make that bold and underlined. Why not? Okay. Now, what are vectors, right? A vector is any force, right? And we don't need this to be bolded and underlined. A vector is any force which has a direction, right? You can see that all of these arrows are pointing in different directions to imply where that force is going. And it has magnitude as well. Now, magnitude is essentially the amount of force, right? So you can see these arrows that I've drawn here. Imagine if I wanted to, go faster down this hill. What I would do is I would just push a greater amount, right? My legs would just put more force in, which extends the arrow, right? So in order to represent greater force, I just use a bigger arrow. Now, if I am pushing my legs with this much force, the result is going to be me going quite a bit faster, right? As you can imagine. So, this is essentially the basics of what vectors are, right? So vectors are any sort of force that has a direction, right, and a magnitude. So the vector of my legs in the uphill is very upward right, you know, with a certain level of force. The force of gravity is downward. And then the blue here is actually what we're going to call a resultant force. The resultant force is the result of a combination of forces, right? It's what happens. It's where my body actually goes as a result of the force of my legs combined with the force of gravity. Now, what we're going to do is we're going to go take a look at how it is that we're able to determine these resultant vectors. How can we calculate the direction? How can we calculate the actual magnitude of the result based upon the combination of forces? So when we're trying to calculate a resultant vector, we have two different methods. One method called the parallelogram method and another called the tip-to-tail method. They both do something very similar, and they'll both give you the exact same resultant vector. So I'm going to show you guys both methods, but you can go ahead and just kind of settle on whichever method works best for you in the end, right? So the parallelogram method, the idea is that if I have two vectors affecting myself while I'm running, here's me running, here's the ground. I have two vectors affecting me. One is gravity, one is my legs pushing me to run. I can draw a parallelogram using both of these vectors. Remember, a parallelogram is that quadrilateral which has parallel sides. So here is a copy of the running vector down here, and I'm going to make a copy of the gravity vector over here. And you can see that the two copied parallel vectors are meeting right over in this spot. And what's going to happen is that is actually going to be the end of my resultant vector, the beginning being where the two vectors started, right? So what is my resultant vector? It is actually going to be 1, 2, 3, 4 units to the right. So you can see that this gravity vector combined with this running vector resulted in this here resultant vector. So I'm going to write that resultant vector. And we're going to go ahead and place that guy. Oopsie. We're going to go ahead and place that guy right on over here, just so that we have it labeled. Okay. Now, that's the parallelogram method. So you can see it creates a nice little parallelogram. It looks kind of cute, right? Next up, let's see the tip-to-tail method. It works pretty much the exact same way. In fact, we basically used the tip-to-tail method to make this parallelogram. So what I'm going to do for the tip-to-tail method is I'm going to essentially just match the tip, right, the end of one of my vectors with the tail of my other vector. So let's take my gravity vector and we're going to throw it onto our running vector. So what I'm going to do in the tip-to-tail method, I'm going to say, okay, running vector takes me up 3 into the right 4. The gravity vector will then start here. I'm going to start it here. And what does gravity do? It goes down 3 units. So I'm going to go down 1, 2, 3 units. So you can see that the tip of the running vector has matched with the tail of the gravity vector. And where did I end up? Oh, who knew? 1, 2, 3, 4 units to the right. So my resultant vector is once again directly to the right, 4 units. Now, you can see that no matter which method I used, I ended up with the exact same resultant vector, 4 to the right. really what both of these methods are doing can be shown mathematically. They're just adding vectors. They're just adding the components. What are the components of gravity? It's 3 down. So I have 3 down. I'm going to call that 3 down right there. What are the components of my running vector? It is up 3. So I have 3 down plus 3 up. And it went to the right 4 units, right? So plus 4 right. Well, how else could we represent, left, right, up, down? We all know that if this was a x-y axis, for example, left and right would be the x-axis. So what you can do is actually, with vectors, we tend to imagine ourselves on an xy axis. And we have our x-axis, and we have our y-axis. Here is the positives. Here are the negatives for the x. Here are the positives for the y. And here are the negatives for the y. So really, 3 down is like negative 3y, right? If you think about it, it's like minus 3y because I've gone down 3 units on the y-axis. 3 up, that's plus 3y. 4 right, that's plus 4x's, right? Because I'm going positive in the x direction. And if I were to add all these up, what do I end up with? Oh, minus 3 plus 3 cancels out. And I'm left with 4x, which is the equivalent of 4 units to the right. So I lied to you, actually, I guess. I said there were 2 methods, but really, this is a third method, the mathematical method, which is going to, in the long run, prove to be very useful for us to be able to do. So if you're ever trying to combine vectors and you're trying to find the result, you can use the parallelogram method, you can use the tip-to-tail method, or you can just add up the components of the vectors themselves and you'll get the result right here.